Okay, so I thought I'd try something new. I'm not connected to the University of Oxford in any way, and I'm just going to engage with their free maths notes, which are online. Don't know if it will be successful, don't know if I'll want to do it long term, but I think. Anyway, let's get started. Introduction to complex numbers. Okay, section 1, the need for complex numbers. It is well known that the two roots of the quadratic equation x squared plus bx plus c equals 0, where a, b, and c are real and a is not 0, are x equals minus b plus or minus 2a. That's the quadratic formula. I know that off by heart. And mathematicians have been solving quadratic equations since the time of the Babylonians. When the discriminant b squared minus 4ac, that's the expression under the square root sign, when the discriminant is positive, then these two roots are real and distinct. Graphically, they are where the curve y equals ax squared plus bx plus c cuts the x-axis. When b squared minus 4ac equals 0, then we have one real root and the curve just touches the x-axis here. But what happens when b squared minus 4ac is less than 0? Then there are no real solutions to the equation, as no real numbers squares to give the negative b squared minus 4ac. From the graphical point of view, the curve y equals ax squared plus bx plus c lies entirely above or below the x-axis. As you can see here, this is where we have distinct real roots. In this case, it's apparently 0 and 2. So this may be from the, let's see, this may be from the quadratic x times x minus 2, rather y equals x times x minus 2. In other words, y equals x squared minus 2x. That's what that could be a graph of. This one here could be a graph of y equals open brackets x minus 1 all squared, which would turn out to be y equals x squared minus 2x plus 1. And this could be all of that plus 1, as in it's been translated 1 unit to the right and 1 unit up. So x minus 1 all squared in brackets plus 1, which is x squared minus 2x plus 2. Distinct real roots are repeated real root and complex roots. It is only comparatively recently that mathematicians have been comfortable with the roots in Formula 1, which is the quadratic formula, have been comfortable with the roots in the quadratic formula when the discriminant b squared minus 4ac is less than 0. During the Renaissance, the quadratic would have been considered unsolvable, or its roots would have been called imaginary. But if we imagine root of negative 1 to exist, and that it behaves, adds and multiplies much the same as other numbers, then the two roots in Formula 1 can be written in the form x equals a plus or minus b times root of negative 1, where a is negative b over 2a, which makes sense, just partitioning the fraction into two pieces, And b is the square root of 4ac minus b squared all over 2a. Notice that they swapped b squared and 4ac around to force b to be positive, real, the positive and real version of itself, and root minus 1, which is I, takes care of that. But what meaning can such roots have? It was this philosophical point which preoccupied mathematicians until the start of the 19th century, when these imaginary numbers started proving so useful, especially in the work of Cauchy, that the philosophical concerns ultimately became side issues. We shall from now on write I to stand for the square root of -1, though many books, particularly those written for engineers and physicists, use J instead. The notation I was first introduced by the Swiss mathematician Leonhard Euler in 1777. All right, definition 2. A complex number is a number of the form a plus bi, where a and b are real numbers. We will usually denote a complex number with a single letter like z or w. If z equals a plus bi, where a and b are real, then a is known as the real part of z and b as the imaginary part. We also write this, that a is the real part of z and b is the imaginary part of z, re and im. When we write let z equal a plus bi, we will implicitly assume that a and b are real, so that a is the real part of z and b is the imaginary part of z. All right, so examples I can think of: 5 plus 3i, 5 is the real part of z. Rather, I should say, let z equals 5 plus 3i, then 5 is the real part of z, and 3 is the imaginary part of z. Okay, not 3i, 3. 3 is the imaginary part of z. Another example, -2 plus 7 over 5i. -2 is the real part of z, if that's z, and 7 over 5, I think I said 7 over 5, that's the imaginary part of z. Anyway, note that real numbers are complex numbers. A real is just a complex number with 0 imaginary parts. We write C for the set of all complex numbers. This is blackboard bold. And it's just, obviously it goes in line with this when I write that for the natural numbers, that for the integers, this for the reals, rather, actually, I should say this for the rationals, and R, a blackboard bold R for the reals, and then this for the complex numbers. Right, so I'll worry about titling my notes in a second, but for now I'm just going to carry on. So one of the first major results concerning complex numbers, and which conclusively demonstrated their usefulness, was proved rigorously by Argand in 1806. From the quadratic formula in Formula 1, we know that all quadratic equations can be solved using complex numbers. What Gauss was the first to prove was the much more general result. Okay, and now we come to the fundamental theorem of algebra. So we're going to let P of Z be a polynomial of degree greater than or equal to 1 with real or complex coefficients. So in the FTA, Fundamental Theorem of Algebra, I might be imagining that P of Z, for example, looks like this. That's a polynomial of degree 2, and as you can see, A0 is just plain old real number, A1 is a complex number, and so is A2. And now I'm going to imagine a cubic. Of course, you don't have to put the brackets here like this. I could just do a minus sign there, but I think it's easier on the eyes to look at this. A0 in this case is purely real, and A1, A2, A3. So A3 is purely imaginary. And, you know, I could also then put in plus z to the 5. And in that case, it doesn't have a z to the 4 term, and the coefficient of that would just be 0. Is 0 purely real, purely imaginary? I guess I don't know, but I think people would just say purely real. But anyway, let's see what now that we understand that, let's look at the main claim of the fundamental theorem of algebra. It says, given that we have P of Z, that polynomial right there, over the complex numbers, then the roots of the equation P of Z equals 0 are themselves complex. That is, there are n, not necessarily distinct, complex numbers, gamma 1 all the way up to gamma n, such that the polynomial that we're imagining of degree n can be written in this form. Okay, so think of when you factor a quadratic, a non-monic quadratic, like 3x squared add 5x add 6, or just think of a non-monic quadratic like this. You can always do this. And now we have a monic quadratic in the brackets. And if we broaden our idea about factorization to not just be over integers, but to also include rational numbers, then you can imagine actually factorizing this into x minus gamma 1 times x minus gamma 2. And we could actually genuinely pursue what those numbers are right now. We could actually do that. All right, so well, let's do it. Let's actually do it, right? So let's see. Okay, so all I'm thinking about is that monic quadratic right there. So I'm going to say minus 5/3 plus or minus 5/3 squared minus 4. Well, I guess that would be what times 1 times 2. And then all of that is divided by 2 itself. Now, 5/3 squared is 25/9. And then I've got to take away 8 from 25/9. So, well, that's the same as taking away this. No, it's not. What am I saying? Am I actually even getting this right? Oh, right. Okay, I made an error. Whoops. Okay, it's that. And then that would be that. So that's actually kind of pleasant that it has 9 there, because that would mean it's root 47/3 times I. So the numerator of that thing up there becomes minus 3 plus or minus root 47/3 I. And then both of these are divided by 2. So put a 6 there and a 6 there. And okay, so then we have like the 2 roots. Now we have the 2 roots, don't we? So gamma 1 would be, whoops, like gamma 1 would be this, and then gamma 2 would be this. Yeah? Okay. In particular, the theorem shows that a degree n polynomial has, if you count repetitions, n roots in the complex numbers. Okay, so the proof of this theorem is far beyond the scope of this text. Note that the theorem only guarantees the existence of the roots of a polynomial somewhere in the complex numbers, unlike the quadratic formula, which determines exactly the roots. The theorem gives no hints as to where in the complex numbers these roots are to be found. Section 2. We're going to look at their algebra. We add, subtract, multiply, and divide complex numbers in obvious, sensible ways. To add or subtract complex numbers, we just add or subtract their real and imaginary parts. Okay, so as you can see, a plus bi plus c plus di. What we do is we add the real parts together to get the real part of the sum. And we add the imaginary parts together to get the imaginary part of the sum. And for the case of subtraction, a plus bi minus c plus di, we find the difference of the real parts to get the real part of the difference, and then the difference of the imaginary parts to get the imaginary part of the difference. Note that these equations are entirely comparable with adding or subtracting 2 vectors in the xy plane. Unlike with vectors, we can also multiply complex numbers by expanding the brackets in the usual fashion and remembering that I squared is equal to -1 by definition. Okay, so when you multiply it out using FOIL or just a table or just your mind, you get this here. But you need to clean it up, put all the real parts over there on the left and all the imaginary parts over there on the right. And we get this. AC minus BD, that's the real part. AD plus BC, that's the imaginary part. So F and L, so it's kind of like, if you think of FOIL, it's like first minus last. That's the real part of my complex number. And then outside plus inside, that's the imaginary part of my complex number Z. Now, to divide complex numbers, we firstly note that C plus DI times C minus DI is simply equal to C squared plus D squared. This relationship here is called conjugacy. That first complex number, C plus DI, and that second complex number, C minus DI, are conjugates. And when you multiply a complex number with its conjugate, it's the sum of the squares of the real part and the imaginary part. And it's entirely real. And the way that you actually carry out complex number division is you multiply the numerator and denominator by the conjugate of the denominator. And then you get this fine result here. So you might want to compare it to what you get from the product. So in the real part, instead of getting the difference, we actually get the sum. We get the sum. And in the imaginary part, instead of getting the sum, we get the difference. But what kind of a difference are you talking about? Well, I'm talking about inside minus outside. And then it's over the sum of the squares of the real and imaginary parts of the denominator, complex number in the denominator. But anyway, so first example, we've got to calculate the sum, difference, product, and quotient, I guess, of these complex numbers here. So, okay, let's just get on with it. So 1 plus 3i plus 2 minus 6i. That would be 3 for the real part, minus 3i for the, minus 3 for the imaginary part. Now, the difference, negative 1 for the real part, 3 for the imaginary part, and the product. Oh, whoops. Hold on. Did I really just do that? Okay, it's supposed to be a plus sign there. Okay, let's take care of this. So minus 1 and 9. Thanks. And now 1 plus 3i times 2 minus 6i. Like I say, this is going to be 2 minus minus 18, which is 20. And then 6i minus 6i, so that's minus 12i. And now 1 plus 3i over 2 minus 6i. So let's times the top and the bottom by 2 plus 6i. Now, on the top, we get 2 minus 18, which is minus 16. And then 12i. And down here, the outside and inside will cancel out by design. And then we have 4 plus 36, which is 40. And this can simplify, or be simplified rather. So we have minus 16 over 40, which is minus 4 over 10, which is minus 2 over 5. That's the real part. And then 12 over 40, which is 3 over 10. And there's my imaginary part there. Okay, so let's check. Okay, first one's right. Second's good. Hold on. Did I mess up here? All right, let's do this one again for the multiplication. So, okay, the real part's totally fine. So we get 6i there and minus 6i. Okay, so actually they cancel out and we get something that is purely real there. Hopefully I did this fine. And I did. Okay, that's great. Division of complex numbers is very similar to the method of rationalizing a surd. Recall that to write a quotient such as 2 plus 3 root 2 all over 1 plus 2 root 2 in the form q1 at q2 root 2, where q1 and q2 are rational numbers, then we multiply the numerator and denominator by 1 minus 2 root 2. Okay, so that's rationalizing the denominator. The number c minus di used in Formula 5 as relating to c plus di has a special name and some useful properties. So I've already said it's the conjugate, but we're going to see that in proposition 18. Now, let z equal a plus bi. The conjugate of z is the number a minus bi and is denoted as z bar or sometimes z star. Note z is real if and only if z is equal to z bar. Also, the real part of z is z at z bar over 2, and the imaginary part of z is z minus z bar over 2i. Okay, is that self-evident? Formula 6? Well, I feel more comfortable proving it. So, here's the claim. So what we have to do is we have to let z equal a plus bi. Z bar is equal to a minus bi. And the real part of z is equal to just simply a. Now, z plus z bar all over 2. Well, let's see. That would be a plus bi plus a minus bi. When you add these up, it seems self-evident now that it's just, yeah, you get 2a over 2, which is a. Likewise here, like by design, that's going to eliminate the real parts. The imaginary parts get added together, and you get bi, and then another bi there, and so you get 2bi, and you have to divide that by 2i, and you get b, and so that makes total sense now. Note that two complex numbers are equal if and only if their real and imaginary parts correspond. That is, z is equal to w if and only if the real part of z is equal to the real part of w, and the imaginary part of z is equal to the imaginary part of w. This is called comparing real and imaginary parts. Note from equation 2 that when the real quadratic equation ax squared plus bx plus c equals 0 has two complex roots, then these roots are conjugates of one another. More generally, if z0 is a root of the polynomial p of z, where the coefficients a, k are real, then its conjugate z0 is also a root. All right, so that's that part of the fundamental theorem of algebra, or like a corollary, which just says that the complex roots occur in conjugate pairs. Okay. We present the following problem because it highlights a potential early misconception involving complex numbers. If we need a new number I as the square root of -1, then shouldn't we need another one for the square root of I? However, z squared is equal to I is just another polynomial equation with complex coefficients, and two roots in the complex numbers are guaranteed by the fundamental theorem of algebra. They are also quite straightforward to calculate, in fact. All right, so we've got to calculate the square root of I here in example 8. So let's give it a shot. Maybe I shouldn't actually say that. That's not actually true, maybe. So it's saying, or asking rather, solve z squared is equal to I. Okay, so what I'm going to do is I'm just going to treat it like an ordinary quadratic. Or am I? Actually, maybe that's not the best idea, because I think it will just end up asking the same question again when I do the QF. So what I'm going to do instead is I'm going to pretend that I already have the solution, a plus bi, and I'm going to square it, and I'm going to set it equal to I, and then I'm going to do this, comparing real and imaginary parts. So when I do that, I'll have a at bi times a at bi, and that, as we've just seen, is a squared minus b squared for the real part. And then we get plus 2ab all times I equal to I itself. Now, What this tells us is that, first, that a squared minus b squared has to equal 0. And second, that 2ab has to equal 1. So just comparing real parts and imaginary parts, because don't forget this I here is just 0 plus 1i. Okay, so given these two facts, what? Well, they're equal square numbers. Okay, so a is 1 over 2b. And so we have wait, am I being really foolish? I don't know why I'm doing that. AB is just a half. So it's the square root of a half, isn't it? Or if you like, root 2 over 2 plus root 2 over 2 times I, and then negative root 2 over 2 minus root 2 over 2i. So I think that's the answer. But then we're going to see what they did. Okay, good. They compared real and imaginary parts and they got the simultaneous equations. And b is equal to plus or minus a from the first equation. And then they substitute b is equal to a into the second to get that. And b is equal to negative a into the second to get that. All right, so that's a lot better, a lot more brief, to the point, and good. Okay. So we get something like what I say here. Yeah. Notice, as with the square roots of real numbers, that the two square roots of I are negative one another. And this is generally the case. However, it's typically the case that neither of the two square roots is more preferential than the other. So we reserve the notation root z, denoting a preferred choice of square root of z, for a positive number z, and define root z to be the positive root of z in such a case. Further, the following rules, x times y all to the r equals x to the r times y to the r, and x to the r times x to the s equals x to the r plus s, hold true for positive x, y, and real r, z. It's unclear what these rules might mean for complex numbers, let alone whether they are true. Below is a famous fallacy of mathematics which shows care needs to be taken with powers of complex numbers. All right, so here we're going to see a fallacy. Clearly, minus 1 over 1 is equal to 1 over minus 1. That's true. So let's just take the square root of both sides. Now, we've been told that the square root of a over b is equal to the square root of a over the square root of b. Okay. So what does that mean? That means on the left, we're going to have I over 1. And on the right, we're going to have 1 over I. But when you rearrange this and you cross multiply, you get that I squared is equal to 1, which is plainly false, because by definition, I squared is equal to negative 1. So that's a clear fallacy. Can't do that. Okay. So in this example here, they're using the quadratic formula to find the two solutions of this quadratic equation over the complex numbers. They're simply setting a equal to 1, b equal to negative 3 minus I, and c equal to 2 plus I. And then they're finding the discriminant. Okay. And the discriminant is exactly 2i. And they know that we know now that the square root of I is plus or minus 1 plus I over root 2 from what we just calculated. And so we see that plugging everything in, we get this as a result, either 2 plus I or 1. Note that the two roots are not conjugates of one another. This need not be the case when the coefficients a, b, and c are not all real. Section 3, the Argand diagram. The real numbers are often represented on the real line, each point of which corresponds to a unique real number. This number increases as we move from left to right along the line. The complex numbers have two components. Their real and imaginary parts can be represented on a plane. Indeed, the complex numbers is sometimes referred to as the complex plane. But more commonly, when we represent C in this manner, we call it the Argand diagram. In the Argand diagram, the point A, B represents the complex number a plus bi, so that the x-axis contains all the real numbers, and so is termed the real axis. And the y-axis, contains all those complex numbers which are purely imaginary, that is, having no real part, and so is referred to as the imaginary axis. So there you can see the Argand diagram on the left, and there you can see Cartesian and polar coordinates on the right. Let's see. Okay, Argand diagrams are named after the Swiss mathematician, trying to say his name, Jean-Robert Argand, although the Norwegian mathematician Caspar Wessel had previously had the same idea for representing complex numbers, but his work went unnoticed. Well, we're noticing it now. Okay, so we can think of Z0, which is A plus BI, as a point in an Argand diagram, but it is often useful to call it, to think of it as a vector as well. Adding Z0 to another complex number translates that number by the vector A, B. That is the map sending z to z plus z0 represents a translation, a units to the right and b units up in the complex plane. Note also that the conjugate z bar of a point z is its mirror image in the real axis. Okay, that makes sense because the conjugate of a plus bi is a minus bi, and so gets reflected like this. The mirror image in the real axis. So the map z that sends z to z bar represents reflection in the real axis. We shall discuss in more detail the geometry of the Argand diagram in section 5. Now, complex number in a complex number z in the complex plane can be represented by Cartesian coordinates. Its real and imaginary parts x and y. But equally useful is the representation of z by polar coordinates r and theta. If we let r be the distance of z from the origin, and if z is not 0, we let theta be the angle that the line connecting z to the origin makes with the positive real axis, then we can write this. So this is sort of like a translation from the Cartesian version of, or rather the rectangular version of the complex plane to the polar version of the complex plane. And that makes total sense. The relations between z's Cartesian and polar coordinates are simple. Yes, indeed, they are that x is equal to r times cosine of theta, and y is equal to r times sine of theta, and r is the square root of x squared at y squared, or the square root of a squared at b squared, if you're more used to that. And tan of theta, the tangent of theta, is equal to y over x, of course. Opposite over adjacent. The number r is called the modulus of z and is written absolute z, or modulus z. I believe that's how you say that. If z is equal to x plus yi, then modulus of z is equal to the square root of x squared at y squared. Note that the modulus of z is greater than or equal to 0 for all z, and that if the modulus of z is equal to 0, then then the complex number z itself is equal to 0. And of course, also note that the modulus of the real part of z has to obviously be less than or equal to the modulus of z, and likewise for the imaginary part. Now, the number theta is called the argument of z and is sometimes written as arg z. So if z is equal to x plus yi, then the sine of the argument of z is equal to y over the modulus. And the cosine of the argument of z is equal to x over the modulus. Now, why does that make sense? Well, you can just think of the definition of sine and cosine via a unit circle. And it's simply saying that the sine of an angle is equal to the opposite over the hypotenuse. The hypotenuse in this case is just how far away the complex number is from the origin. That's the denominator. And the opposite is y. The cosine, same story. Adjacent is x. Yes, adjacent is x, and the modulus of the real number is the hypotenuse, the length of the hypotenuse. Okay. Finally, the tangent of the argument of the complex number is equal to y over x. Note that the argument of 0, the complex number 0 itself, is undefined. Also note that the argument of z is defined only up to multiples of 2 pi. For example, the argument of 1 add I, which we can just visualize as is pi over 4. But, we could also say, but wait, isn't it also 9 pi over 4? Or possibly negative 7 pi over 4? Well, here, pi over 4 is the preferred choice. As for definiteness, we shall take the principal values for the argument to be in the range of 0 to 2 pi. So just remember that theta always has to be from 0 to 2 pi, and you know how to get it within that range. For ease of notation, we shall write CIS of theta for the expression cosine of theta plus I sine of theta, so that complex numbers in polar form, as in Formula 7, will now be written as z is equal to r CIS theta. Now, cis, we're just going to say cis. Okay, so that's cosine of theta plus I sine of theta. In due course, we will prove Euler's famous result, e to the I theta is equal to cosine of theta plus I sine of theta. And so write the polar form as r times e to the I theta after that. Now, here we have a proposition 17. And it says, let alpha and beta be real numbers, then cis of alpha plus beta is equal to cis of alpha times cis of beta. And in conjunction, it says all right, so I'm going to assume that yeah, no, okay, fine. Cis of alpha bar is equal to cis of negative alpha, which is also equal to 1 over cis of alpha. All right, so for the first conjunct of the proposition, cis of alpha plus beta, we have to recall the definition. So that's cosine of alpha plus I sine of beta. And what does that mean? So where are we actually going with this? So we're going to cis of alpha times cis of beta. Oh no, that's actually completely wrong what I wrote up there. That's just super wrong. That's wrong with the cape on. It's this. All right, so it's that. Okay, so I think I can go somewhere with that now. So we have to recall the angle addition formulae. So I believe now we're going to attempt to record them first, and then we check. So I believe sine of A plus B equals sine A cos B plus cos A sine B. So I believe it's this. And now I have to check. Right, for example, 0 at 90. Right, so that just turns to 1. And then that's 0. Okay, that's 0. Okay, so that just seems fine. Now we check. We've tried, and now we check. Okay. Right, that's fine. That's for the first part. And now for the second. Sine alpha cos beta. Plus cos alpha sine beta. And somehow this has to reduce to that. I know that if I were to just write out what the right-hand side is, okay, we'll just do that. That's the left-hand side. And now we're going to have a look and see what the right-hand side looks like. Pardon me. Cis alpha, cis beta. Well, that's equal to cos alpha plus I sine beta by definition. That's the first factor. The next factor, sorry, beg your pardon, it's supposed to be alpha right here. The next factor is cos beta plus I sine beta. Okay, and now if we multiply everything out using first outside, inside, last, we get cos alpha, cos beta for the first. And for the last, well, let's see. Sine alpha times sine beta, okay. And then I times I, well, that's minus 1. So minus sine alpha, sine beta. And then for the inside, it's kind of obvious if you see it. Sine alpha cos beta plus cos alpha sine beta. And there you go. So that is for the first conjunct. Now, let's think. How did they do this? So it's not good for me to do what I did here, unraveling the left side and then unraveling the right, because I think you're supposed to go from left to right or from right to left. Pick a lane, you know? And what they did was they went from the right side to the left side. And I appreciate that because doing it that way, it seems kind of like, oh, I can recognize, when I group the real parts together and the imaginary parts together, then I just sort of like recognize that side of the formula. It feels more natural. Yeah. Okay, now for the other stuff. Now, I just glanced and I saw a single line for their proof. So the conjugate of cis alpha, well, by definition, that would be the conjugate of cos alpha plus I sine beta. And again, I'm not paying attention or I'm going on autopilot. There. Cos alpha plus I sine alpha. Okay. And then this is cos alpha minus I sine alpha. Okay. And let's think. Now, fundamental property that we're permitted to take for granted. Cis of negative alpha, isn't it? That's true. But also, it's equal to the reciprocal of cis alpha. It's also equal to the reciprocal of cis alpha. So the conjugate of cis alpha is equal to the reciprocal of cis alpha. Okay, so we're going to go from right to left. Times the top and the bottom by the conjugate. Here, now outside and inside cancel by design. Then we have cos squared alpha, sine squared alpha, but that's times by I squared, which is also times by -1, so it becomes plus. And on the top, cos alpha minus I sine alpha. Pythagorean identity, that is just simply 1. This here is not cis of alpha, but rather the conjugate of cis of alpha. Okay, all right. And there, okay, now we have some super important properties. Wait, oh my goodness me, there's 12 of them, 12 independent ones. Okay, so oh man, I'd love to go even further, but I do know that it's very useful for me to actually prove those propositions. So what do I think about this? I've only done a little bit, a real super tiny bit, but hasn't it just been lovely? I've really enjoyed this. Yeah, so I don't have any sort of grand ambitions or plan to do all of this, because obviously these are notes and courses for full-time students at super selective and high-end universities. But nonetheless, I mean, I think that these are, I found it really pleasant. So yeah, I might actually, I might do this. I would like it if I can just simply get to the end of some of the problem sets, and I mean, you just find out more as you go if you like it. So I've got to page 7, and I'll wrap it up there. Be well, be well.